In the previous video, we have gone through an introduction of Wi-Fi security, and we have touched on WEP in the context of WEP-based authentication. In this video, we will cover more of the details of how WEP works. But before that, I want to go back to a slide from the previous video on open authentication, because in there I had mentioned about MAC address filtering. Recall that in MAC address filtering, the access point can have a list of MAC addresses that it chooses to allow into the network, or a list of MAC addresses that it chooses to deny access to. And then when requests come in, it can check the list and choose to either deny or allow the request. MAC address filtering is one of those things that it can be helpful, because then you can keep certain devices out of your network or allow only devices on the approved list into your network. So in a small office or home environment, it's a perfectly reasonable thing to do. But we need to be aware that it's not foolproof. MAC addresses are supposedly unique and not something that a user can change, but devices are available and software is available that allows MAC addresses to be spoofed. So an attacker could get his hands on one of these devices, and then once he has learned what MAC addresses are allowed into a network, he can just spoof this MAC address and then get into the network as well. So we have to be careful about MAC address filtering. It's useful in certain contexts or if part of a multi-layer security solution, but beware that it's not foolproof. Anyway, now let's move on to look at WEP. WEP stands for Wired Equivalent Privacy, and it's used for both authentication and privacy in Wi-Fi systems that implement it. This is actually not a best practice, because you should be using different keys and different protocols and algorithms for authentication than for privacy. In modern systems, you don't find the same mistake repeated, but that was years ago when WEP was introduced, and for various reasons it was done this way. Now, one of the reasons is that WEP was not really meant to be super strong. It's not meant to be military security. It's just meant to be something that's reasonably strong, reasonably being a very subjective term, yes. But back then, the observation was made that with wired LANs, there is some kind of authentication in the sense of the wire being connected to the local area network, whereas in wireless you didn't really have that same kind of even basic authentication. So therefore WEP was introduced, but it was not very strong, and purposely so, for reasons like the export control laws of the US at that time, and also to make it more easy to implement in low-cost hardware and software. WEP uses RC4, which is a stream cipher invented by Ron Rivest, a famous cryptographic expert. And RC4 itself is not a terrible encryption algorithm. The weaknesses in WEP have to do more with the way in which that RC4 is used. I mean, it's a building block used in WEP, and the way in which it's used is not very strong. For example, originally there were these 40-bit keys that were used. You might hear that the keys were actually 64 bits, but it depends on what you mean by the keys, because you have 40 bits that are variable and then 24 bits of the so-called IV, initialization vector, which in some systems were never changed or was a well-known sequence of initialization vectors. So effectively then you only have 40-bit keys. Later on, 128-bit keys were added as an option, but in that case you still have the same 24-bit initialization vector. You subtract that away and you get 104 bits of variable bits. So it's either 40-bit or 104-bit keys. Here's a block diagram of how WEP works. Let's take a look at this top part first. So this is the preparation for encrypting the plain text. We have the initialization vector as I mentioned and the secret key, so 40 bits or 104 bits of secret key and then 24 bits of initialization vector. This forms the seed to the pseudo-random number generator used by WEP. This then results in a key sequence which is XORed, bit by bit XORed with the plain text. Well, not exactly the plain text, it's the plain text that's appended with an ICV, integrity check value. This integrity check value, or ICV, is meant to provide data integrity protection so that on the receiver side, the receiver will know whether the data has been modified in transmission. So other than that, then it's a bit by bit XOR of the key sequence with the plain text to give you the ciphertext. So it's relatively simple to describe, and that's what we have here. The initialization vector is also sent together with the ciphertext in the message, so on the receiving side the receiver will know how to decrypt the message, because then the receiver can, if the receiver has the same secret key, the receiver is then able to generate the key sequence given the IV, and then can do another bit by bit XOR to get back the original plain text.